Hello and a warm welcome to calculating ionisation energy from wavelength and wavelength from ionisation energy. The IB chemistry data booklet has two equations which are pretty unhelpful. One is C is V lambda and the second is E equals HV or mu, depending on your enunciation. We know that C is the speed of light, V is unhelpfully the frequency. I wish to make that F, but there we go. And then lambda, as you know from your GCSE physics, is indeed wavelength. There are clearly some units conversions we're going to have to be concerned about within converting between these three units, but we can do that and we'll have a look at that today during this video. So why not use V equals F lambda IB? Over to you. Answers in the comment box below. Thank you. E equals HV, moving on to this one, E is the energy of a single photon. Single being the operative word, because we're often given data in kilojoules per mole or mole of photons, so we have to invoke Avogadro's constant 6.023 by 10 to the 23. H is Planck's constant 6.63 by 10 to the minus 34. Yes, I have a head for numbers, but these are in the data booklet. And V is frequency, as it is on the left. So because frequency appears both times in each of these equations, we can combine these equations together to make them more useful for us in an IB chemistry setting. So combining, E equals hc, Planck's constant velocity of light over lambda, the wavelength, and lambda is hc over E. These are the most useful forms of those two pretty useless equations without any explanation they give you in the data booklet. Let's see how we're going to use those. So firstly, let's have a look. There are only two ways that the IB can ask this question. First of all, we're going to look at a problem where we are given the first ionisation energy of a metal, and we have to work out the wavelength or the dissociation, or the wavelength at convergence limit, or the wavelength at infinity level. They are all interchangeable between each of those three quantities. So we want to end up with a wavelength. It can be in meters or nanometers. Both will be acceptable on the mark scheme. You have to know the difference between meters and nanometers. Okay, the difference is 10 to the minus 9. Okay, nano 9 is kind of helpful. It alliterates and it's almost the same word, so that's good. So which process are we talking about? We're talking about a neutral atom going to one positively charged, unipositively charged gaseous ion plus one electron. The question will give you the first ionisation energy. In this regard, it's given us the first ionisation energy for gold. I thought gold would be an interesting one for this video. It turns out it's 890.1 kilojoules per mole. If it gives me the ionisation energy, it can pretty much only ask me what is the wavelength. It's not going to ask me what's the value of Planck's constant or the speed of light, because they are in the data booklet, and those are the only other two quantities in the equation. What's my first step? Well, initially I need to work out the energy for one photon. Okay, I've got 890.1 kilojoules and I want that in joules. So that's 890,100 joules per mole, and that per mole is interesting, as you will see very shortly. So I take my 890,100 and I want that for one photon, so I need to divide that by Avogadro's constant, which is 6.023 by 10 to the 23, as every man, woman, child and Mr. Gardner knows, and that gives me an answer of 1.478 times 10 to the minus 18 joules. So now I've got the energy for one photon. I need to get that somehow into wavelength. The only other equation I can use is hc over E. H is Planck's constant, c is the speed of light, and E we've just worked out in the preceding step as 1.478 times 10 to the power of minus 18. The numbers are quite cumbersome. They're not friendly in any way, so make sure you hit the buttons on the calculator correctly. So if I times joule seconds by meters per second divided by joules, I get an answer in meters. Handily, this is going to give me an answer for the wavelength of 1.345 by 10 to the power of minus 7, there goes the battery sign, meters. Okay, I've taken out joules, I've taken out seconds, the only thing left are the meters. Remember that nanometers I said at the beginning of the video, meters to nanometers, 10 to the minus 9, well, that makes it 134.5 nanometers. Where does that put that wavelength? In the UV part of the spectrum. The only other direction they can ask you to work out is to work out the ionization energy from a given wavelength at the convergence limit. Remember, that is the limit where the electron actually leaves the neutral atom, forms the ion, otherwise known as the first ionization energy. Let's hope we get it somewhere close to the data booklet value. So the convergence limit for sodium is 242 nanometers. Okay, we're going to use C is lambda V. C is the speed of light. We're given lambda in the question, but again, this is going to be in nanometers. We want this to be in meters because the speed of light is in meters per second. Okay, that's going to give us V, that's going to give us the wavelength, it's going to give us the frequency, it's going to give us the frequency, so it's going to give us an answer of 1.24 by 10 to the power of 15 per second, otherwise known as hertz. E equals hv, using the second equation, so we've got Planck's constant, times our frequency we've got from the previous one, which is 1.24 by 10 to the 15. And it's another uncomfortable number, which is 8.22 by 10 to the minus 19 joules. Remember the last one we had to divide by Avogadro's number? Well, now we have to times because we're in a different direction. So that uncomfortable joules number we times by 6.023 by 10 to the 23 because we want it per mole of electrons, not just for one electron. That actually gives us quite a good number, a healthy number, and that gives us a number of 495 kilojoules per mole. I just looked up the literature value and it's 496 kilojoules per mole. So well done us. If you didn't understand, review this video. Thanks very much for watching. Comment, like, subscribe at the bottom. Bye.